by the vector, by the tensor. So if T transforms U and T transforms V, it is TC that transforms U cross V. That is, you can find U cross V from U and V alone by just transforming that area by TC. Or you can also find the area by taking the cross product of TU times TB, but you can ignore the tensor T entirely by just simply transforming the area by the cofactor, and you are going to get the correct result, because the cross product of TU and TV is the same thing as the cross product of U and V transformed by the cofactor. And that is what really defines a cofactor. And every other definition that you will see of a cofactor can be obtained from this idea. So the idea of a cofactor is that is what transforms areas when a tensor transforms lines. Once a tensor transforms vector lines, the areas are transformed by the cofactor. So the cofactor is what you need to resort to when you are interested in finding area. And this is very, very critical in engineering. In fact, if you have any loaded structure, what happens to that structure is that there is a stress field there. What that simply means is that at every point there is a stress tensor. Similarly, there is a strain tensor, because that when there is stress, the thing is strained. Now, if you now know what the strain tensor is, that is, you know the value of the strain tensor at every point. If you now want to know what happens to the area, you just need the cofactor. The cofactor will tell you what happens to the area, whereas every elementary line there was transformed by the strain tensor, but the areas are transformed by the cofactor. So the cofactor has a serious physical meaning, and it is that makes it so important. So if you want to know anything about cofactor, it is this equation that defines the cofactor. That is, TU cross TV is equal to TC operating on U cross V. So TC is what transforms the area U cross V. So every areas are transformed by the cofactor. Before the end of today's class, we will also see what transforms volumes. Now you will see that if you have an elementary area like a parallelepiped U dot V cross W, and you now transform each of the vectors forming it, you will find out that it is not that same tensor that is transforming the volume. It's something else that's transforming the volume. Like if you have area and the vectors on the area are transformed by T, it is the cofactor of T that transforms the area. If you have a volume and T is transforming the lines that make the volume, it is the determinant that transforms the volume. You will see that later on. So that's why when you have a tensor, you have its cofactor, you have its determinant. And in fact, the invariants of a tensor are related to this. The second invariant is the trace of the cofactor, and the third invariant is simply the determinant. So you can see why those things are critically important. It is very instructive and useful for an engineer to look at these things from the physical point of view and then derive all the mathematics from that physical point of view. It keeps you close to what you are after, which is to solve physical problems with this, not just to have plenty of mathematics in your head. Okay, so when vectors U and V are transformed by the tensor T to TU and TV, then the vector U cross V is transformed by the cofactor. Now, the next thing we did is to go and formulate the components of the cofactor. And we arrive at this equation here, which says that this complicated expression, which gives us a whole number of terms. Let me just check whether the class is awake to ask how many terms do we have here? How many terms do we have here? Well, you are right, there are 9, but each of the 9, because there are essentially two independent indices here, which is so you are correct, there are 9, but each of the 9 has a multiplicity of numbers that make them up. But You can always use the summation convention and eventually arrive at what that is. I told you to go home and confirm that this expression is correct. If you go to the, so it's one of the solved problems in the book. So that I don't need to go through that again. Okay. So we now move from there to the next page. In the next page, I concluded last week that the second invariant, which is the trace of is simply TMM TNN minus TMN TNN. And I said this is the square of the trace minus the trace of the square. Now, why is this quantity the square of TMM and TNN? Can anybody tell me why? Why is it the square of the trace? Go to the chat room. Is it obvious that this is the square of the trace and that this is the trace of the square? Is it obvious to the class? Is it obvious that this first term is the square of the trace and the second term is the trace of the square? Are we clear on what those things mean? Please, I want you to tell me if it is clear, if it is not clear, so that I would know what to do quickly. Okay, it is clear that this is the square of the trace. Yes, and that the other one is the trace of the square. Good. Well, if it is not clear to anybody, I have worked it out here. I worked it out here. So just go here. It's already in the book, but if it's not obvious to you, go through this. And I hope you can see what I worked out here. Before I leave this page, I want to see whether the class understands why what I cross out with red mark here, why it is wrong. Why TII squared is not TII times TII. Can somebody tell me why this is wrong? Why it would be wrong to say TII squared? Remember that TII is a scalar, so it can be squared. Why TII squared is not TII TII? Can anybody tell me why? Why is it that TII squared is not TII TII? I'm waiting. Waiting. Please go to the chat room and tell me why TII squared cannot be equal to TI, but it is equal to TII TJJ, but it's not equal to TII TII. Yes, James, what about the convention principle? What particular thing about the convention principle? Yes, it is about the convention principle. Because of the dummy indices, yes. What's about the dummy indices? You are close, but you have not said it. You are just on the periphery of it. Yes, that is it. You cannot have the dummy index repeat more than once. You can't have more than two of them. So if you are going to have TII, you better change this one so that there is no appearance of dummy index more than twice. And once you have more than two dummy indices in your expression, I don't need to look further. You are already wrong. So there's no. So instead of TII, it's TII TJJ, which is the same thing as what we have here, which is written as TMM TNN, the same thing. So this one is TIJTJI or TMN TNN, the same thing. So this is the square of the trace, and this is the trace of the square. So, and this is the proof of that, which shouldn't have been necessary, but just in case it is hard for you to immediately understand, I've worked it again out for you to see here. So that is the same thing. So it should be obvious to you when you see TMN TNN that is the square of the trace, and then TMN TNN, that is the trace of the square. So in textbooks, many textbooks, they define the second principal invariant as the trace of the square minus the square. So that the square of the trace minus the trace of the square of that same tensor. So this is what is taken as the definition. We don't take it as the definition, we prove that it is just by taking the by taking this, you see that it is this second invariant, which is the trace of the cofactor. That's what it gives you. Now, the next thing, or which is the last thing in this note, is to show that this definition of the cofactor that we have got, that it is the same thing as the original, that the other definition we did first. The only problem, the weakness of the, can somebody remind us what is the weakness in this definition of the cofactor? We find the cofactor as the inverse transpose of T multiplied by the determinant of T. What is the weakness of this definition of the cofactor? If we define the cofactor like this, what is the weakness of this definition? Can anybody remember and tell me what the weakness is? Not all tensors are invertible, but we can find the fact that the tensor is not invertible doesn't mean it doesn't have a cofactor, but this one presupposes that the tensor is invertible. But in case the tensor is invertible, this is also the cofactor of that tensor. What we are doing now, we are now proving that if the tensor is invertible, this will also be the cofactor of the tensor. And so we begin from this definition, that is TU cross TV is sitting as cofactor operating on U cross V. So once we have that, we can now go and prove that this is also correct, which is what we are doing now in the next few slides. If T is invertible, the independence of the vectors U and V, if U and V are linearly independent, then TU and TV are also linearly independent. If you don't know why, go to question 2.24. We have already proved that there. So if U and V are linearly independent, TU and TV are also linearly independent. If TU and TV are linearly independent, that means they are not. Okay, let me just find out whether you know. If TU and TV are linearly independent, what does that mean physically? What does that mean? That they are linearly independent. If two vectors are linearly independent, what does that mean? What does that mean? What conclusion can we draw about them? If TU, which is a vector, and TV, which is another vector, if they are linearly independent of each other, what conclusion can we draw about TU and TV? Kamal, you are correct. They cannot be expressed as a linear combination of the other. Well, you cannot talk of linear combination. Can you talk of linear combination of one vector? You cannot be talking of linear combination of one vector. It's only if there is more than one vector. We are just talking of only two vectors now. Yes. If you, what I'm saying is that what do we know if the two vectors are linearly independent? What do we know now about those two vectors that are, what does that mean? Okay, let me be a little bit more specific. What does it mean? What does it tell us about the area of the parallelogram that they can form? If those two vectors are made to form a parallelogram, what can we say if the two vectors are linearly independent? What can we say about the parallelogram that they form? If two vectors are linearly independent, what can we say about the parallelogram that they form? If I say two vectors are linearly independent, whether it's U and V or TU and TV, what can I therefore say about the parallelogram that they form? The parallelogram area is the cross product of the vectors. I agree, but what can I say? Is there any judgment I can make about what that cross product will be like? Is there anything I can say about it? No, it is not. It's a vector. Every area is a vector. So that's nothing. That's not nothing to do with the fact that the vectors are linearly independent. This is if we do not settle this matter, whatever else, we are just working. Yes, James would not talk. The area cannot vanish. Because if they are not linearly independent, they can be collinear, and the cross product will be zero. If two vectors are collinear, their cross product will be zero. The vector points in direction. No. What we are saying is that if two vectors are linearly independent and they form a parallelogram, that parallelogram must have a non-trivial area. The area cannot be zero. That is the thing, because if two vectors are linearly independent, they cannot be collinear. Two vectors that are collinear are not linearly independent. If these two vectors are linearly independent, it means they are not collinear. They are not along the same line. So if they are not along the same line, therefore, their parallelogram must be non-trivial. They cannot form a trivial parallelogram. They cannot form a parallelogram with an area of 0. Okay. Now, since it took so much time for you to give me this answer, and you are not talking, so I want to expand the question beyond what I need immediately. Okay, I've changed the question because you didn't answer that first question fast enough. I want you to tell me, if I tell you that 3 vectors are linearly independent, what can I say about the parallelepiped formed by the 3 vectors? What can I say about the parallelepiped formed by the 3 vectors if they are linearly independent? The value of what? Oluwatobi, the value, which value? The value of what is not 0? Yes, James will not talk again. If 3 vectors are linearly independent, then the volume of the parallelepiped they form cannot be 0. The volume is another way is to say the volume is not trivial. David and Nigbo, you cannot talk about the cross product of 3 vectors. You can't talk about that. It's nothing like that. Is this the scalar triple product we are looking at here? When we talk of 3 vectors, it's when we are talking of 2 vectors, we are talking of the cross product. When you are talking of 3 vectors, talking of the scalar triple product. That is V dot U cross W or V cross W, V cross U dot W. So that gives you the volume is non-trivial. That is, it's not 0. Because if they were linearly independent, then they can be coplanar. If they are coplanar, their volume will be 0. Similarly, if 2 vectors are collinear, the area of the parallelogram that they form will be 0. But once you say that 3 vectors are linearly independent, physically, what it means is that they have a non-trivial parallelogram. And because they have a non-trivial parallelepiped. If it's 2 vectors, they have a non-trivial parallelogram. Because, of course, you can still form a parallelogram by 2 vectors that are collinear, but it's just that it's just a parallelogram in name only. It's not a real parallelogram, because if it was a parallelogram, the area cannot be 0. But we say that's trivial. It's not a real parallelogram. Okay? So when 2 vectors are linearly dependent, the area of the parallelogram between them is not 0. If 3 vectors are linearly dependent, the volume of the parallelepiped between them is not 0. That is that these things are not trivial. So let us go back. Well, please, these things are important because these are the things that drive the mathematics. The mathematics you are rushing to do makes no meaning unless you understand the basis or the things that actually undergird and underlines them. Okay, so we are saying that if we start with 2 vectors, we can take 2 arbitrary vectors U and V and assume they are linearly independent. If they are linearly independent, we proved in question 2.24 that if you transform them by by an invertible tensor, that means that the TU and TV are also linearly independent. And if TU and TV are linearly independent, it means that TU cross TV is not 0. Since TU cross TV is not 0, and it is a vector, we represent it by a vector n. And we say that that vector n is not equal to 0. And because the class has been quite dull this morning, so I'm still going to ask you another question to wake you up. This 0 I have here, is it a vector 0, a scalar 0, or a tensor 0? The 0 I have at this place, is it a vector 0, a scalar 0, or a tensor 0. This last equation, the 0 I have on the right-hand side, what type of 0 is it? Vector, tensor, or scalar? Oh my, the class is awake. Okay, good. So you can see that this 0 we are talking about here is a vector 0, because since TU is a vector, TV is a vector, their cross product is also another vector. So when we say it's not 0, we are saying it is not the 0 vector. The 0 vector contains 3 scalar zeros. So that's why we cannot confuse one for the other one. So that's it. So you are correct. Now the class, now I'm a bit happy that the class is awake, because before you were all snoring. I can almost hear your snore through the Zoom. Okay, so since it's vector n is not 0, so that means that, and it must be perpendicular. Do you agree, before we go on, vector n is not 0, do you agree that it is perpendicular to TU and it's also perpendicular to TV? Because since it is TU cross TV, it must be perpendicular to both of them. It's perpendicular to this one and it's also perpendicular to this one. Since it is perpendicular to both of them, if we take the dot product of n and TU, we should get 0. If we take the dot product of n and TV, we should also get 0. That is what we are writing next. So that means that n dot TU is equal to 0, and n dot TV is also equal to 0. Now, class again, what 0 do we have on the right-hand side here on this first equation? Is it a scalar 0 or a vector 0? This equation here. What 0 is this? Scalar, vector, or tensor 0? On the first equation on this page. Scalar 0. Good. Okay. My students are smart. Good. Good. Okay. So if we recall the definition of the transpose, if we reverse the order of this and we say instead of n dot TU, if we write u dot something n, you can see that this is what we define to be equal to what we had before. It is what we define as the transpose, just reversing the vectors in this triple equation. So in this equation that has two vectors and a tensor. So if this is true, it also you can transpose this equation and know that this is also true. So if this is true, this is also true, showing that TTN is perpendicular to both. So what we have on this side, you have TTN dotting V giving you 0, the same TTN dotting U giving you 0. So if that is the case, that means that TTN must also be perpendicular to U cross V, since it is perpendicular to both U and V. So TTN is a vector and it's perpendicular to U and it's also perpendicular to V. So we can write it is some constant, is some scalar multiple of U cross V. So if it is perpendicular to both U and V, then it must be along the line or the perpendicular to both U and V. And therefore, we don't know alpha, but whatever alpha is a scalar. So we can write that TTN is equal to alpha into U cross V. So with that, we can now go back and remember the definition of n was TU cross TV. That's the definition of n. If that's the definition of n, we can say that we can replace n here by TU cross TV. And that's all we have done to this equation. So where we are now, we have just replaced n by TU cross TV, which is what was defined as n previously. So that is it here. So what will we have after once we have reached this place, we can therefore write that if you take any vector W that is linearly dependent of U and V, then we can take a scalar product of the above equation. You see, we have this equation here and we want to take what we have here. The totality of what we have here is a vector. Why? Because TU is a vector, TV is a vector. And therefore, TU cross TV is also a vector. And then if you apply a tensor on it, you still get a vector. So if you have another vector W that is linearly independent of U and V, so we can take its dot product of W with this expression. So we take dot product of W with the expression on both sides. So if we do that, what we then have is that W dot TU cross TV is equal to alpha U cross W dot V. So again, we can take this vector to the other side. We take this vector to the other side, and then we will remove, because the transpose of a transpose is the original tensor. So we can therefore write here that this is written as TW dot TU cross TV. So T now operating on W is equal to TU cross TV dot TW. That is what it is. So in the equation, TU cross TV dot TW, we have equal to alpha U cross V dot W. It is clear from this expression that the alpha that we did not know before is simply the determinant of T. Just look at this expression. If you look at this expression, you will see that the alpha is the determinant of T by definition, because the determinant of T, if you do not remember, just remember that the determinant of T is TU cross TV dot TW divided by U cross V dot W. So if that is the case, this equation shows that alpha here is the determinant of T. Therefore, we can change alpha to the determinant of T and just have this expression as we have set out to do. So if we look at, if we change alpha here to the determinant of T, once we change alpha here to be the determinant of T, then in this expression, we can now, this last expression now becomes that the TU cross TV is the determinant of T times T inverse transpose into U cross V. So, and this question, that means that what we have at the beginning of this now is simply the cofactor. This quantity now is simply the cofactor, because we are told that TU cross TV is simply the cofactor operating on U cross V. So this is the cofactor, which proves the first definition we gave. So we can derive that first definition from the fundamental definition that the cofactor is the determinant of T, which is a scalar, multiplying the inverse transpose of the tensor. So you want to know the cofactor of a tensor, take its transpose, and so take the inverse, transpose it, and multiply it by the determinant. That will give you the cofactor of the tensor. So we have gotten the cofactor from these three definitions now. We have arrived at the same thing, provided from the same place. Okay. So we now move. We conclude this chapter with the idea of that. Let's see what our time is. Okay. We will look at orthogonal tensors. In our study of tensor properties, we encounter some interesting tensors. The table here shows some of these tensors as we classify them into two groups. We are looking at the tensors we looked at originally. There were 7 of them: projection, vector, cross, spherical, annihilator, dyad, identity, coordinate rotation. We know that all tensors transform vectors. But when the vectors are transformed, we know that we'll get new vectors. How do those vectors relate to the original? We can never be sure. Okay, substitutions, we know that in the annihilator, it will just give us 0. So that one is, in spherical, it will just multiply the vector by a constant. But in other cases, we cannot predict what will happen. But in identity, we know that it will do nothing. It does absolutely nothing. In the coordinate rotation, all we get is a rotation. The magnitude is preserved, but it just rotates the vector. So the tensors in the first group change the magnitude of the vectors they transform. The second group are tensors that create the transform vectors of the same magnitude as the input vector. The second group are 2 members of a distinguished class of tensors, and we need to spend a little time to know them better, they are in a class called orthogonal tensors. Tensors that we know they change when they operate on a vector, they will change the vector, quite all right. But if they change the vector without changing its magnitude, we say that that kind of tensor is an orthogonal tensor, and it is important to take some look at orthogonal tensors. Orthogonal tensors are tensors that transform in such a way that they can change the vector, but they will not touch its magnitude. We call such a tensor an orthogonal tensor. Okay, so let us take a look. Now, I have a question here for you. Please, class, wake up. You are going to answer another question. The more you seem drowsy, the more questions I'm going to throw at you. We know that a transformation that does nothing, I, and a transformation that rotates, preserve magnitude. Is there any other magnitude preservation transformation you can imagine? One that does nothing, of course, will preserve the magnitude. One that simply rotates, of course, may not preserve the direction, but will still preserve the magnitude. Can you tell me what you can physically do to a tensor that will also not change the magnitude, but it's not one of these two? For instance, you know that projection will not only change the direction, it will also change the magnitude. But rotation will not change the magnitude. Identity will not change the magnitude. Is there any other transformation you can imagine that will not change the magnitude? I want you to think. If you say there is none, say so. If you think there is no other one apart from those two, say so. I want to see whether you can imagine any other transformation. If you have thought about it and you cannot think of any other one apart from the identity and the rotation, can you imagine any other preservation, magnitude preservation transformation? Is there any other one apart from identity and rotation? Oluwa Tomiwa said, I don't think so. Okay, that's that. Who agrees with Oluwa Tomiwa? Toluwa, no, sir, I can't. Okay, can't think of any. Do we agree, therefore, there is none? Can we say there is no other thing? There is no other transformation that can preserve magnitude from rotation and modulus. Modulus is not a transformation. It's not a transformation. Well, that's not a transformation. Oh, yeah. Okay, class, there is one. I am telling you now that there is one. And I'm okay. Ginika, can you said there is. Which one is it? Ginika says there is one. Laplace. funny man. A coordinate transformation, we have said, that is a rotation. A coordinate transformation is a rotation. Ginika, coordinate transformation, that's what we have here. Orthogonal transformation, that's what we are talking about. We are going to call all transformations that are magnitude preserving, we are calling all of them orthogonal transformation. We have already identified two. One is the identity, the second one is the second one is the rotation. Is there any other? Okay. When I tell you this other one, you are going to knock yourself because you will think you are a fool for not remembering. It is so, by the time I tell you, you will all think you should have known it. I'm happy I didn't tell you immediately. No, it's not a spherical transformation. A spherical transformation indeed changes magnitude, unless the spherical constant is 1. The spherical constant is usually not 1. Spherical transformation does not change. A spherical transformation changes magnitude. Okay, what's projection? Projection changes magnitude. Don't you know that in the sun, if you during the day, in the midday, the sun is under your legs, which means that it is 0 magnitude. And in the night, as the night is coming, it's continuously increasing. It's a cylindrical, is that something called a cylindrical transformation? I don't know about that. Okay, I'm going to type the name of the transformation and I will see. Can you see it now? Can you see it? Is it not obvious that reflection will not change, can change magnitude, can change direction, but cannot change magnitude? If you reflect a vector, yeah, it's obvious. Yeah, see, Gochuku, why did you tell me that before? It is now obvious. Okay, so before we go into too much mathematics, know that when we talk of orthogonal tensors, essentially we are talking of three transformations: transformation by identity, transformation by rotation, and transformation by reflection. It is those physical transformations, those three things, that constitute what we mean by orthogonal tensors. Orthogonal tensors are either the identity tensor, the rotation tensor, or the reflection tensor. You will see we can always form a reflection tensor. We can put mathematics into it and give you something that when we transform any vector, what you will get will be a mirror image of it. That's a reflection tensor. So just like you could get a projection tensor, there is a reflection tensor. Okay, so when we talk of orthogonal tensors, you can just relax and know that all we are talking about mathematically are those three things: identity, rotation, and reflection. So whatever mathematics you do, at the end of the day, it's not going beyond those three transformations. Given a pair of vectors A and B, an orthogonal tensor Q is said to be, a tensor Q is said to be orthogonal if QA dot QB is equal to A dot B. Specifically, if we allow A to be equal to B, so QA dot QA is equal to A dot A. So if you take the magnitude of A and take the magnitude of QA, they will be the same. So that means that the magnitude of A is preserved by the transformation. So the fact that you have applied Q to A did not change the magnitude from what it was before. As we can see, one important attribute of the orthogonal tensor is that the magnitude of the input and the magnitude of the output is the same. We are not saying that the vector input is the same as the vector output. We are only talking about their magnitude. The vector may have indeed changed. The vector might have changed. It might have changed in direction, but it did not change in magnitude. When a tensor does that, and it is magnitude preserving for the vector it operates on, such a magnitude preserving tensor is called an orthogonal tensor. That is the definition. What is an orthogonal tensor? An orthogonal tensor is the magnitude preserving tensor transformation. That's it. And examples are identity, rotation, and reflection. So let Q be equal, let Q A. So the transpose, from this expression here, in these two lines, we prove that QTQ, if we operate Q on its transpose, you get the identity. So the Q is not the identity, but QT, the product of Q, the composition of QT with Q gives you the identity. So, and that can be proved. That is proved on these two lines. A condition necessary and sufficient for a tensor to be orthogonal is that the tensor is invertible and its inverse is equal to its transpose. So one property of orthogonal tensors is that if you want to invert an orthogonal tensor, don't waste your time going through the difficult process of trying to get an inverse. Just transpose it. The inverse of an orthogonal tensor is its inverse. So in some books, that is used to define what an orthogonal tensor is. But with the definition we have, we can always get that on that definition. Every orthogonal tensor possesses an inverse, for sure. If a tensor doesn't possess an inverse, it cannot be an orthogonal tensor. And the inverse is simply the transpose. Every orthogonal tensor can be transposed, and the transpose is the inverse. The determinant of an orthogonal tensor. This page we can show that the determinant of an orthogonal tensor is either plus or minus 1. The determinant can be plus 1 and it can be minus 1. Upon noting that the determinant of a product is the product of determinants, we know we saw it before, that the determinant of a product is the product of determinants. If QTQ is equal to identity tensor, then the determinant of QTQ is equal to 1 because the determinant of identity is 1. We are starting from this expression here. Where is the expression? We are starting from this expression here. QTQ is equal to I. So the determinant of QTQ is the same thing as the determinant of the identity. The determinant of the identity is 1. The determinant of the identity is 1. So the determinant of QT times the determinant of Q, which is the same thing as, because the determinant of Q and the determinant of QT are the same. So that's the determinant squared. If the determinant squared is 1, that means that the determinant is either plus or minus 1, because you cannot conclude that the determinant is 1, because minus 1 squared is still going to give you 1. So that means that the determinant of Q can be plus 1, can also be minus 1. That observation leads to another definition. The definition it leads to is that when the determinant of an orthogonal tensor is strictly positive, when it is plus 1, we call that orthogonal tensor a proper orthogonal tensor. So an orthogonal tensor is a tensor that preserves magnitude. A proper orthogonal tensor not only preserves magnitude, it still has a determinant of plus 1. So when those two conditions are fulfilled, we say the tensor is not just orthogonal, but it is proper orthogonal. In particular, a rotation is a proper orthogonal, but a reflection is an improper orthogonal. It's not a proper orthogonal. So a rotation is a proper orthogonal. An identity is a proper orthogonal. A reflection is not a proper orthogonal. I've never seen any textbook call it improper. I'm the person just saying that. So don't take me seriously. We just say it's proper orthogonal or it is not proper orthogonal. So you can see that identity is proper orthogonal. Rotation is proper orthogonal, but reflection is not proper orthogonal. Why is it not proper orthogonal? Because its determinant is minus 1. So let us see one other interesting thing about orthogonal tensors. Another interesting thing about orthogonal tensors is that they are self-cofactor. If you are looking for the cofactor of an orthogonal tensor, its cofactor is itself. The cofactor of an orthogonal tensor is itself. So, for any pair of tensors, we want to show on this page that Q into U cross V is the same as QU cross QV. This question is the same as showing that the cofactor of Q is Q itself. Now, all you need to do is to remember the definition of cofactor we have just come about. We know that cofactor is just the determinant of Q, but multiplied by Q raised to Q, the transpose of Q inverse. Now, if it is proper orthogonal, then the determinant and the Q, since the inverse is the same thing, the cofactor is Q. So just look at this. Since if Q is a rotation, the determinant is 1, and Q inverse transpose is Q inverse transposed. Q inverse is Q transpose. The transpose of the transpose is the original tensor. Therefore, T is equal to Q. So proper orthogonal tensors are self-cofactor. What about improper orthogonal tensors? Orthogonal tensors that are not proper orthogonal. They are not self-cofactor. Their cofactors is their negative. So that is the thing. Proper orthogonal tensors are self-cofactor. You can't say the same thing of not proper orthogonal tensors. So it therefore means that one eigenvalue of a proper orthogonal is always 1. We will go into, let me see how much time we have to see whether we can go into eigenvalue today. No, we will not. So it means that QU is equal to U. There is always a solution for that. Since for any invertible tensor, the cofactor is this equation. For the proper orthogonal tensor, determinant is 1. And then we can form the characteristic equation. But I don't want us to go into the eigenvalue issue until we properly talk about it. The last thing on this thing is the axial vector. Let us just take a look at the axial vector. The vector cross is a skew tensor. This fact can be seen by transposing and showing that the transpose, it is negative. Like all skew tensors, it is a traceless tensor. Now the question, given a skew tensor, can we find a vector that the tensor is a vector cross of? When this happens, the vector found in this way is called the axial vector of the tensor. Given a skew tensor, can we find a vector that the tensor is a vector cross of? Note that in either case, there are only 3 components. This is obvious from the vector. For the skew tensor, once 3 independent components are found, the remaining are simply negatives of the independent components. So from week 6, if you go to slide 26 in week 6, we define the vector cross. We define the vector cross as this quantity. So the question is, given that this is a vector cross, can we solve the above equation for V? Can we solve this equation and find Vk in terms of the components of omega ij? We can, sure. We can begin from saying that minus eijkvk is equal to omega ij. If we have something like this, if we let us see, because look at it here. Look at this expression here. If we look at the definition of the vector cross, this expression is true. So if you multiply both sides by E alpha ij, we have this. And therefore, Vi is equal to minus half Eijk omega jk. So this is the relationship between the axial vector, which is a vector, and the axial vector, and then the tensor, the skew tensor. Every skew tensor can be converted to a vector, and every vector can be converted to a skew tensor. That's what we have here. We are how many minutes into the time? We are 52 minutes. What I'm going to do for you today, class, is this. I don't have time to give you a break. Instead, we are going to go to the next set of slides, but I'm only going to take you 20 minutes into the hour. So you will be free from 12:20. So I think that is what I can do for you, since I cannot afford to give you a break right now. I have somewhere to go. So I'm going to start with the next set of slides, and then we will discuss more next week. So let me change my slides now.